if you are working with fractions that are mixed numbers, please change those to improper before you do anything else. So we're going to change this one to 24/5 times 5/4. So change your numbers, mixed numbers, to improper first. Then this ends up being an extremely simple question. Reduce before you multiply. My 5's cancel. My 4 goes into 24 6 times, and I'm left with the square root of 6, which does not have a perfect square, which does not break up. You're done. So, as difficult as it may look to start with, it's not a difficult question if you change those numbers and reduce. If you multiply it and then try to rationalize it and all that kind of stuff, then you've created a monster there. The next couple questions I just want to hit on nth roots. I did not do or will not do any nth roots that you have to rationalize. That's a whole nother ball game. Okay? So all our nth root questions should be ones that are pretty simple, reducible, or square rootable, not square rootable, rootable, okay? But go through your same questions. Can I perfect cube these numbers? No. Can I reduce this? Yes. So I'm going to have the cube root of 3 goes into 81 27 times. And then remember what to do with the powers. 8 minus 3 leaves me x to the 5th. So reduce the fraction first, and then simplify. So the cube root of 27 is a perfect cube. That's 3. And then 3 goes into 5 one time with 2 left over. And don't forget that little root symbol. So 3x cube root x squared. Same approach on the next question. Do these have perfect fourth roots? They do not. Can I reduce it? Yes. 3 goes into 48 16 times. And I can reduce my powers and take 11 minus 7, leaving me x to the 4th in the denominator, though. Remember that if the power is bigger in the denominator, when you subtract the powers, that's where they're left. That goes way back. And then these have perfect fourth roots. The fourth root of 16 is 2. And 4 goes into 4 one time with none left over. Anything on those nth roots? Okay, so here's where we change it up. You're going to notice that in my denominator, I have an expression that's not a single radical, which means I cannot rationalize this radical in the denominator by just multiplying by square root 2. I have a sum or a difference. Okay, in this particular one, I have a difference. I have subtraction. So it's as simple as it can go right now. There's nothing that you can do that you know of to that question. Square root 3 over 3 square root 2 minus 3 is as simple as you can get it without rationalizing it. Okay? So you have to get rid of that denominator. So the other day I talked about the concept of conjugates. Okay? And conjugates were two expressions whose first terms and last terms were the same with the opposite sign. In fact, let me go back real quick to those notes so I can point out what happened on those. So remember what happened on those. When we multiplied something by its conjugate, the outers and inners cancel each other out every time, and it also eliminates the radical term. So when you take something times a conjugate, it gets rid of the radical. So there's where that concept comes in here. I have to get rid of that radical. So I'm going to have to multiply this question by the conjugate of the denominator, which is 3 square root 2 plus 3. So it's the exact thing that you see in the denominator with the opposite sign. If you don't use the opposite sign, it doesn't work. And again, I got to put it over itself to make it equivalent to 1. So you take what's in the denominator and you change the sign in the middle. That's what you're multiplying by. You'll know to do this on the kinds that have addition or subtraction in the denominator. Okay? So in my numerator now, I'm going to distribute because I have square root 3 times this. So square root 3 times 3 square root 2 is 3 square root 6. Square root 3 times 3 is 3 square root 3. Now, I don't FOIL when I multiply something by its conjugate because I already know that outers and inners are going to cancel, so I don't waste the time. So I just do first times first and last times last. So first times first is 9 square root 4, and last times last, 3 times 3 is 9. Simplify. The square root of 4 is 2 times my 9 is 18. So I get 3 square root 6 plus 3 square root 3 over 18 minus 9, which is 9. I'm not finished. We've eliminated the radical though. That was our goal for rationalizing. You then need to see at this point if you can reduce it. Okay? So I'm going to give you a way that's kind of weird. I made it up. You'll be able to tell I made it up. Okay? To reduce something. So this is how you can tell if you can reduce something. You look for what I term as Mickey Mouse ears. Okay? So, and I visually do this, but I'm going to physically do it to show you what I mean. So you look at these numbers. Okay, so I look at those numbers, and if they all have a common factor, you can reduce it. And they do. They all have a common factor of 3. So I can make this 1 square root 6, or just square root 6, plus 1 square root 3, or just square root 3, all over 3. So I look at the coefficients in the numerator with the number in the denominator, and if all of them have a factor, they all have to have it. If they don't all have it, it can't be reduced. So that's my final answer. Okay, in my next question, I'm going to have to rationalize. There's no simplifying to do on these questions before you just go right to the rationalizing. So I'm going to have it times 4 plus the square root of 6. In the denominator, same expression with the opposite sign. That's the conjugate. In my numerator, I do need to FOIL. So first times first is 4. Outer times outer is 1 square root 6. Inner times inner is 4 square root 6. And last times last is the square root of 36, or just 6. I like to split the 6. In my denominator, since I'm multiplying something by its conjugate, I don't need to FOIL, and I won't. 4 times 4 is 16, minus last times last, the square root of 6, times itself is just 6. And I simplify. In my numerator, I can add 4 and 6 is 10. 1 square root 6 and 4 square root 6 is 5 square root 6. In my denominator, 16 minus 6 is 10. check for Mickey Mouse ears. In this particular one, I don't have two radical terms, but I'm looking at the two terms in the numerator. So the coefficients, 10 just doesn't have anything behind it. If they're all reducible by a common factor, which they are, of 5, I can reduce this. So 5 goes into 10 twice, so 2. 5 goes into 5 once, so I just have 1 square root 6, or just square root 6. And 5 goes into 10 twice for my final answer. And then my last one. My conjugate from the denominator, 5 square root 2 plus 4. Change the sign or it doesn't work. So I FOIL in the numerator. 5 times 5 square root 2, 25 square root 2. Outer times outer, positive 20. Inner times inner, 20 square root 6. And last times last, 16 square root 3. And in my denominator, again, first and first, last and last. 25 square root 4, 5's on the outside, 2's on the inside, minus 16. So 25 square root 4 is going to simplify to the square root of 4 is 2, times my 25 is 50. So my numerator, I can simplify not a single one of those things. I can't combine them. I can't break it up. I can do nothing to anything in that numerator. In my denominator, I take 50 minus 16 and I get 34. Now this particular mouse has 4 ears because I'm checking this and this and this, and this, and this, to see if I can reduce it. So 25, 20, 20, 16, 34. They do not have anything common to all 5 of those numbers. So that answer is done. You don't have to go any further. And again, I wouldn't be circling those physically. I would just visualize that. Okay? So visualize that answer without the circles and that's your answer.